Hi, this video covers a technical issue in our C++ implementation of the singly linked list. We actually need to create a custom destructor to prevent a memory leak. So let's understand why that is. Recall that we're using standard shared pointer as the pointer to every node object. It's not the most appropriate thing in a way because unique pointer might make a little bit more sense because these node objects are uniquely owned by the list object. The problem is that we have a circular list, and that means that the tail node needs to have two pointers into it. And the rule with unique pointer is it's unique. You can only have one pointer to an object. So as a workaround, we're using a shared pointer. The way that shared pointer works is it uses reference counting, which means that when we have shared pointers to a node, the shared pointer class is responsible for keeping track of how many pointers point at that node. That number is called the reference count or the ref count for how many incoming pointers there are to that node. And if that ref count ever becomes 0, that means nothing is pointing at the node and it's time to delete it. Well, because of how all this works with our circular links, the default constructor actually leaves all the nodes with a ref count of 1, and that means they don't get freed automatically, and we have a memory leak. So we need to solve this, and what we need to do is create a non-default constructor that goes in and makes sure that all of the ref counts to the nodes become 0 so that they become freed. All right, let's sketch how this is happening. So here's our familiar 3-element singly linked list. It's got the circular links. I'm going to draw the reference counts in green. We call these ref counts for short. And visually, the ref count of an object is the number of incoming shared pointers. So the dummy node here has one incoming pointer. It's the circular link. The 7-element node has one incoming pointer. The one in the middle has one incoming pointer. And then the one that's different is the tail node. It has two incoming pointers because there's the next pointer of the second to last node. There's also the list object's tail pointer. So this tail node has a ref count of 2, and that's kind of the source of our problems. Let's see why the destructor fails to free all these nodes. So let's say we destroy the list object. What the default constructor does is destroy all the data members of the list object, including the tail pointer. So that incoming pointer to the tail node goes away. That one of the two incoming pointers to the tail node are destroyed, and now the tail node has a ref count of 1, which is progress, but it's not sufficient to make all of these nodes get freed. These ref counts have to get down to 0 in order for a shared pointer to delete the objects. So we need to fix this. So the solution is we need different behavior, so we need to write an explicit destructor that does something different than this. It needs to guarantee that all the nodes get removed, and we'll write explicit code that does that. That will leave us with a valid empty singly linked list that just has a dummy node. There's still a circular link in there, which is causing ref counts to be greater than 0 when the list is destroyed. So we will also explicitly break the dummy node's circular link. And at that point, the remaining default behavior will free that last node. Okay, so here's what the code looks like. It's relatively simple in concept. So I've got this loop while size is positive pop front. So, that reads pretty well. As long as there are elements left, pop the front one. It's important here to use pop front. Remember that this is singly linked list. Pop front takes constant time. Pop back takes linear time. So in order to make this while loop as fast as we can, we're using pop front, the faster of the two. So that will clear off all of these nodes except for the dummy node. And then there's one last detail, dummy set next null pointer. That changes the dummy node's next pointer to null. So now there's no circularity in any of these links anymore. And the destruction of the single shared pointer to the dummy node will cause that node to get freed. This destructor takes linear time, which is reasonable because it needs to free all n nodes. Let's see how this would run on the same example. So here's the same example, the 714. So first we're in this while loop, and it's going to pop front. So the first node, the 7, gets freed, and now we're down to a size 2 node containing 1 and 4. I envision this as kind of like reeling in, kind of reeling in the nodes, like if you have a fishing pole and you reel it in, or a length of twine or yarn and you're reeling it in. Okay, so we're kind of reeling in the nodes, freeing them one at a time. Size is 2, it's still greater than 0, so we pop the front, which is now the 1 element. We pop the front, which is now the 4 element. That's the end of the while loop. We're down to size 0. At this point, we're almost done, but note that the dummy node still has a ref count of 2 because of the tail pointer plus the dummy node's own next pointer. So we say dummy set next to null pointer, and that will update this ref count down to 1. See, so the list object has 1 pointer to the dummy. The dummy is now pointing at null pointer. It's not a valid way for a singly linked list to be because that circular link is breaking an invariant. This is just very temporarily before the list object is destroyed completely. Okay, then we get to the end of scope of the destructor, and the tail shared pointer gets destroyed, and so that destroys the last remaining incoming pointer to the dummy node. The ref count goes down to 0, and at that point, shared pointer automatically frees the dummy node. So now this works. Now we don't have any memory leak. Okay, I should point out one detail here. The rule of 3 is now coming into the forefront. The C++ rule of 3 says if you define any of these, you must define all 3: the destructor, the copy constructor, and the copy assignment constructor. It's all or nothing with those 3. Either you don't implement any or you implement all 3. You can't do only some. Well, I just defined the destructor. So rule of 3 says to have a class that doesn't have any memory management problems, we need to also define the copy constructor and the copy assignment constructor. And the rule is right about this. Those operations need to make their own node objects. It wouldn't work to have 2 list objects that both have pointers into the same collection of nodes. That would cause confusion when you modify one list or the other. So this rule is right about that. I'm going to leave that as an exercise. I don't want this video to be too long, so we're not going to go into the code for that.